Welcome back, everybody. It's cold? Huh, seems warmer than usual to me, but... Anybody want to share anything fun they did over spring break?
I worked 65 hours.
Holy moly! Wow, so you earned money. That's good. Anybody else? That's okay. Okay.
What did you do?
I visited my parents and my wife's parents with our little guy and spent a lot of good quality time with him at home. So, yeah, he loves being outdoors. So, you just set him down and let him walk and watch out for cars. That's a fun afternoon for me. I'll have to share a video with you guys maybe tomorrow. We were in my shop in the basement, and I was playing with a vise and just moving it around, and he just thought it was hilarious. So maybe we'll watch that tomorrow. It's fun. Okay, so let's take a quick look at the question here. Potential and kinetic energy. This might remind you of your physical science days or maybe even your grade school days. What is the difference between potential and kinetic energy? Yeah.
Is it like potential if I'm holding the water bottle? Kinetic is if I actually drop it.
Yeah, that would be a good example too. So the good way to kind of summarize all this is that potential energy is just stored energy. Kinetic energy is the energy of motion. So potential energy is stored energy. Kinetic energy is when you're moving. So, just to kind of give you an idea of where we're at now, we just finished our massive 4-chapter unit on motion and the laws of motion. So we talked about velocity and acceleration, we talked about inertia, we talked about force, we talked about projectile motion, and now the whole main goal of that was for you to understand not just how things move in the air, but why they do so. And that brings us to this chapter, which is basically another analysis of that, but from a different perspective. So you can solve a lot of the same force problems and a lot of the same acceleration problems from the last couple chapters using energy. Some people find it being easier, some people find it being harder, kind of depends on your personality. So it'll be an interesting chapter for us, but it begins nice and easy, and it stays easy for quite a while. So potential and kinetic energy, as you guys said, it sounds like you probably have a pretty good understanding of that already. And before we go any deeper, I have a very important question. So you can see that I shaved a little bit, and it was really weird because when I shaved it all off, and I looked in the mirror and I was like, man, my face just looks naked. It looks weird. So I thought I kind of got to let it grow a little bit to get a little bit back. So I want to see a little bit of a vote here. Okay, so there's 3 different periods of time with Mr. Hathaway's face. When it was nice and clean shaven and smooth, now with a little bit of stubble, and of course when I had the full beard. So heads down, I want to see some hands here without people worrying about what other people think. Okay, if you thought Mr. Hathaway looked better with a full-fledged beard, raise your hand, please. Thank you. If you thought Mr. Hathaway looks better with a completely clean-shaven, smooth face, raise your hand. If you think he looks better with a little bit of stubble, raise your hand. Okay, thank you. Wow, that was like pretty much even all the way across the board. So, I don't know. Maybe I'll keep it like this. Maybe I'll shave it more. We'll see. Thank you for your input, though. I appreciate that. It has been pretty much even throughout the whole day. Generally, it seems like the guys like the beard, and the ladies like less beard. So it's kind of interesting. I should have kept track of the actual demographics of these votes. Okay, so in terms of energy, as I mentioned, we're going to talk about how kinetic energy works and how potential energy works. And in order to understand these things, we need to see some good examples of them. So when we're talking about potential energy, does this ball have potential energy right here? Absolutely. Because if I let it go, it falls. And that's probably the best way to figure out if something has potential energy. Just ask yourself, if it's released, will it do anything? Will it go anywhere? And of course this ball will, because gravity's going to pull it down. This is a spring. Does this spring right now have potential energy? Yeah. Because if I let it go, it's going to go back and forth like that. And those are really two different kinds of potential energy. This kind is called gravitational potential energy. This would be spring potential energy. For the purpose of the homework today, we're not going to differentiate between the two, but you do have to be aware that potential energy is present for both cases. Now, in terms of kinetic energy, it's pretty easy to see. If an object is moving, it's got kinetic energy. And oftentimes it might start with potential energy, and then when you let it go, or when you release it, that potential energy is going to transfer into kinetic energy. And that's kind of the main thing we want to talk about today. As we see objects going through different, phases and circumstances, we want to be able to map out exactly how that energy is changing over time. So that's going to be kind of what we're doing today. So let's say we have this fancy little thing that you could probably get for like 10 tickets across the street at round one. And I've dealt with this before. Set it down, hold it for a little bit, and it launches upwards. So then the question is, what kind of energy is present at the beginning when it's on the table? Potential energy. What energy is present after it releases? Kinetic, absolutely. It's as easy as that. But it does get, some of these scenarios do get just a little bit more complicated. Not really, though. So let's say we've got, I'm going to raise this in dramatic fashion for the folks at home. Let's say you have the Batmobile from Batman Forever, 1995. And this has a special little spring mechanism on the inside, so that when I pull it back like this, it winds up. And if I let it go, obviously it's going to move, for a little while anyway. So we've got a lot of different kinds of energy going on there. So let's just say if I'm moving it on the table, of course you know it has kinetic energy. The folks at home, it moves like this, it's got kinetic energy. What kind of energy does it have if I back it up like this? It's got potential energy. Now what does it have? Kinetic energy. Very good. Now what energy does it have? Well, let's say that this table's the ground, maybe. It doesn't really have any, right? Like if we're going to say that this is on the ground, and maybe it can't go any further, maybe pretend it's not on a big teacher's table there, then it would have no energy left. So then the question is, where did all that energy go? Anybody know? It disappeared. And it disappeared in a certain way. There's a couple different ways that energy can be added and subtracted to systems. So you don't even need to take notes today if you don't want. This is pretty straightforward. And you actually, this is an introduction to energy being gained and lost. We'll take notes on this tomorrow. Energy loss, one way that you can lose energy is by heating. That's abbreviated with the letter Q for some reason. So when we talk about heating, especially in things like thermodynamics, it's abbreviated with the letter Q there. And what you would find is that if you take this car and you measure exactly what the temperature is on the inside in that spring mechanism before that it's released, and then after, you would find that it is increased in temperature. As it's wound up, as it's compressed, you gain some temperature on the inside of that spring mechanism, so that when it's released and that energy dissipates, it loses it to heat. So it's kind of heating up the car when that happens, and that's where that energy goes. Typically, you lose energy to heat with something that's like bouncing on the table. Like if you have if I take this bouncy ball and it bounces, you'll notice it bounces less and less and less as time goes on. That's because some of that energy is going away. Some of that energy is being transferred into the table via heat. If you could measure the exact precise temperature of this table right now compared to after this thing has bounced a while, you would find that the table gets a little bit warmer. It's kind of strange, but that's one of the ways that energy is transferred between systems. Yeah?
Right, so if it didn't lose the heat or energy or whatever, would it bounce at the same height as it's moving?
Yes.
Or
If
what would gravity do?
Well, you would have all potential energy, and then it's transferring into kinetic, moving faster and faster. Then it hits the ground. If all the energy would remain conserved, then it would come back up to the exact same height. It's the process of this deforming a little bit when it hits the ground. That's where that energy transfer takes place. If you had a perfect ball that bounced perfectly and didn't lose any of that energy, then you would have an exact, bounce right back up to the exact height. Does that answer your question?
Yeah.
And the thing, too, is energy is also lost through vibration. So even if you had something that was perfectly solid, that didn't deform, you would still lose energy through the sound vibration. And that would also go into heat in the ground. So there's really no way around it. You're going to lose energy one way or another. Sonic the Hedgehog. There's a little spring mechanism in here. And if I let the spring go, you can probably guess what's going to happen. Sonic goes flying off at supersonic speeds. So this is going to be kind of an extra complicated example because we're going to say that, yeah, he's off the ground here. So what kind of energy does he have at this moment? Potential. Both spring potential, because it's compressed on the inside, and normal, regular, gravitational potential, because he's off the ground. And, of course, when you let it go, then it's transferred into kinetic energy, then eventually hits the ground, loses some energy to heat, and comes to a stop. Now, to really make sure that we're clear on this and make sure you're prepared for the homework, let's just do one more thing with energy loss, and then we'll jump into some actual examples that you'll encounter. So the other way that you can lose energy is through something known as radiation. That's abbreviated with the letter R. It's pretty rare that you're going to see an example of this in your homework. Basically, you'd have to have something lighting up or starting on fire. Generally, you don't see that kind of behavior in a system. So when you have an object, like if you have somebody rolling down the hill, they probably aren't going to spontaneously combust, as fun as that would be to see. But for radiation, something has to actually be giving off light. Like these lights are radiating. That's one of the ways that they're giving off energy. They're constantly being resupplied by the circuitry in a power source, but they are radiating. If something is on fire, it is radiating. And those are the two ways that we deal with energy loss. Now, Batmobile's here. Here. And it's not moving. So, it doesn't have any energy right now. How am I supposed to get it to move if there's no energy there? I have to add energy to it. Otherwise, it's just going to sit there looking pretty. And the way that we can add energy to a system is by working on it, we say. So anytime energy is added to a system, whether it's by me, in this case, rolling it on the table, or backing it up so it gets a little spring potential energy before shooting off. That's how you get that extra energy. You do work on the system to provide that energy so that it can move. Alrighty. Now the way that you're going to be doing this on the homework is through pie charts. You guys like pie? I like pie too. What kind of pie is your favorite? Cherry pie? I've heard that one several times today. That's a popular one. What else? Pumpkin pie? That's a good one. Anybody else? Nice. Apple pie is good too if it's made right. Because I've always been somebody who really likes lemon flavored things. So when I was a kid and people would ask what kind of pie I wanted, I'd say I wanted a lemon pie, whatever that is. But anyway. So generally we do this with 3 pies. And let's use this as an example first here. So we've got our little spring mechanism sort of thing there. It's on the table, shoots up, and it comes back down. So let's say I want you to tell me what kind of energy is present at the very beginning, when it is halfway up, and when it is at its maximum height. So when it is on the table yet, what is all of its energy? Yep. What about when it's halfway up through the air? Yeah, half and half. Doesn't matter what side you put which energy. And at the end, when it's at the very top of its path, it's all potential, yeah. Because at that top of its path, it is momentarily at rest as it turns around. So it would all have potential energy right there. Very good. Let's see here. Let's do an example with the Batmobile. So we'll say the Batmobile is backed up just a little bit like this, and we'll say that time begins right now. Okay, so at the beginning, what was all of the energy when I was still holding it there? That was all potential, yep. And then once I let it go, what kind of energy did it have? It had kinetic. And it did have a little bit of potential too, because it does take a while for the mechanism on the inside to unwind. If you just put potential for this one, that's acceptable. But yeah, you would have both until the thing is completely unwound. And what kind of energy does it have right now? None. And the way you would mark that is you just put lines through your thing. If you want to make it look like a planet, you could do that too. Whatever. Okay. In order to go through the last example, I'll hand out the homework and we'll just do number 1. Then you can have the rest of the hour. So the one I'd like us to look at here is going to be number 1. Let's go through number 1 together, and then you can just do the rest by yourself. So for the problems on this worksheet, you have to do a pi for every single picture that you see on here. So like number 1, you're going to be drawing 3 pies. Number 2, you'll be drawing 3 pies. Number 3, how many will you be drawing? 5, because there are 5 different spots that ball is. So that's the idea. So for number 1, we're going to be doing 3 of these. So at the very top, you can see the ball is at rest. That's what the dot with no arrows represents. So what kind of energy is present at that location?
Potential.
Yes, it's all potential energy. And then the next one, you can see the ball is above the ground and it's moving down. So what energy is present there?
Kinetic
Yeah, kinetic and potential. Maybe we should make this one into a planet too. There we go. And at the very end, if you look really, really, really close, you'll see that there's a little bit of space between the object and the ground. So that represents the final instant before this object actually touches the ground. So what is all the energy at that point? Yeah, it's kinetic. If you wanted to put a tiny sliver of potential, that would be okay. But the main thing is that you notice that all the energy starts as potential, and then as it goes down, it turns into kinetic. So that's the idea. The last thing I'll mention on this is if you look on number 5, that's probably the trickiest one. As that ball is bouncing, you'll notice it is not just going up and down, it's also going from left to right. So when it reaches the top of its path there, it is still moving because it does have some horizontal motion associated with that. So you do have to take that into account when you're drawing your diagrams. So yeah, that's that. If you have questions, let me know. This will be due tomorrow, but you should be able to finish it with plenty of time to spare in class.